Okay, now that we've done a hydraulic analysis on the penstock, let's look at turbine characteristics. So the turbine is the area where they deal with energy transfer. So in order to go ahead and do that, I'm not going to go through all the steps of this, but what we'll do first is something called a turbo machine dimensionless analysis. So if you look at the different parameters in turbo machinery, right, you have their symbol here. And if you were to go ahead and break them down into basic dimensions, you can do a dimensional analysis. And that dimensional analysis would allow basically to bring forward the following parameters. We have what's called specific speed. So we have specific speed for both a pump and a turbine. So if we were to go ahead and do that, you would end up with these following two equations. Where this W is the angular speed, and this W, so this is omega and this W is work. This is what we would call a traditional analysis or traditional definition. We can also take these and to get them into units that are dimensionless, right? So actually what we're going to do is we're going to be using the following parameters. And in these parameters, we're going to basically set up the equation so that we can use angular momentum in RPM, flow rate in GPM, gallons per minute, head in feet, and work in horsepower. So these equations, these two equations for specific speed are now going to be recast into the following two equations, which are dimensionless and which are what we're going to be using in this class to classify turbines and pumps. So these two equations end up being the following. So these two equations here are the ones we're going to be using. Again, these are specific speeds. This is an equation to compute specific speed. It's non-dimensional. Here we have the parameters used in them along with their units. So these equations have been recast into what I would call dimensionless form. And we're going to basically take these equations as they sit here in order to classify turbines. So if we look at this next slide, you can see on the y-axis we have efficiency versus on the x-axis specific speed computed from the prior slide. And you can see along too on the bottom here, we see the transition from the different types of turbines, starting with centrifugal to mixed flow to axial flow. And as you can see, as the flow rates change, right, your specific speed will increase and the efficiency changes. It also has an effect on the type of turbines that you would pick. We're going to take that graph and actually put it into dimensionless form. We get the following, and this is what we would call the turbine-specific speed relationship. We're going to be looking at basically three basic types of turbines that vary from radial to mixed and axial flow turbines. So here's another graph similar to the one on a prior slide, which is the one that we're going to be using for this chapter. Y-axis is efficiency, and the x-axis is specific speed. You can see that there are basically three types of turbines that we're looking at. One is going to be impulse turbines, actually two classes of turbines, impulse and reaction turbines. And you can see that for low specific speeds, we're going to be using impulse turbines. Then we're going to be moving into reaction turbines as specific speeds increases to two different types of reaction turbines. One is a Francis turbine, which is a turbine that allows radial to mixed flow, ending with the Kaplan turbine, which is a turbine that is more axial flow. So basically what happens is after a hydraulic analysis, you can figure out what your specific speed is, and from the specific speed, you can pick the type of turbine that's suitable for that specific application. So let's go ahead a little further and look at the example of a Pelton turbine. So a Pelton turbine is another way of is a type of impulse turbine, right? So if you go back and we look at impulse turbines, you can kind of see how they work here. We have a nozzle, right, which accelerates the water, comes out as a water stream, and hits what we would call these buckets, and it causes the turbine to spin. These buckets, if I were to go ahead and do an expanded view here, have what's called a splitter ridge. What happens is that the water stream comes, hits the splitter ridge, and the water gets diverted into these two different directions. And it's designed in that way in order to maximize energy transfer from the jet stream to the blade. Francis turbines, again, fall into the range of radial to mixed flow. So you can see that we have water entering into what's called a stay vane, and then the water hits the turbine blades in the radial and sometimes in a mixed flow direction, and as they come out, they get directed into the axial flow region. And then finally, Kaplan turbine, which is completely axial flow. The water comes in and gets diverted in the axial direction before it hits the turbine blades. So those would be the three types that we're going to be looking at. A Pelton turbine, which is another form of an impulse turbine, Francis turbine, and Kaplan turbine. So what I say we should do is just go ahead and let's do a quick example problem here. In this example problem, we're asked that for the conditions in the prior example problem that we went through, where we analyzed the penstock, determine the type of turbine to be installed if the desired rotational speed is 1200 RPM. Right, so if we go back to that problem, we can see that we did a hydraulic analysis on it, and we pretty much computed what the total power being extracted from it, and it's 24 kilowatts. So go back here, we could put that the power extracted is 24 kilowatts, and it looks like, according to the problem statement, the height difference between point A at 915 and point B at 892 is 23 meters. So if we go ahead and we plug in our numbers, I know that, for example, 1 horsepower is 745.7 watts. So if we take our equation for the specific speed of a turbine, again, this is the non-dimensional form, we have angular speed multiplied by work in horsepower divided by the height in feet. So if I go ahead and plug in these numbers, I know that my speed is 1200 RPM. My power is going to be 24,000 watts divided by 745.7 to get that into horsepower. That's raised to 1/2 power divided by my height in meters. I'm going to convert that into feet. I go ahead and I compute that my specific speed, my non-dimensional specific speed, is 30.6. So if I go back to my graph here, 30.6 lands me about here, right on the x-axis for specific speed. That lands me right in the middle of the Francis turbine region. So basically for this problem, again, this is from figure 3.9 in your book, we would end up with a Francis turbine. Okay. All right. I hope that this example problem is clear, and we're going to go ahead and stop this video at this point, and we'll continue with this chapter in the next video. Thank you.